One of the things that we use partial derivatives for, as you can probably imagine, as in brief calculus or your previous calculus course, is to find a maximum or a minimum. Now, this three-dimensional function could represent any number of things. It could be we want to maximize profit or maximize revenue, minimize cost. And so these three-dimensional surfaces, as we call them, this is called a surface. We don't often call them curves. Often will have these local or global extrema. Now in this case, we can see here that this shape is called a paraboloid, and like a parabola, but it's a three-dimensional parabola, so we name it a paraboloid. And so the question is, how do we locate such a minimum? Again, this could represent minimum cost. So in this case, we see that this is indicated as x equals 3, y equals 2, z equals 0. So for inputs of x equals 3 and y equals 2, we could say we get a minimum z value of z equals 0. So far we've thought about partial derivatives and how to interpret them and how they emphasize the rate of change. Now when we think in two dimensions, if we think about a single variable function that just contains x and y, and perhaps that function looks like this, maybe just a simple parabola, concave down, and we can see that at this point there appears to be a maximum. Now from brief calculus, you might remember that the rate of change as you're climbing up this hill, if you imagine yourself climbing up this, then you have a positive rate of change. The slope at any given point has a positive direction. Whereas on the other side, any point has a negative direction. So the slope at this point and the slope at this point may be identical in size, but they're opposite in direction. So here we have positive slopes, here we have negative slopes. Well, what happens at a maximum? Well, at a maximum, when you're standing there, when you're standing at that maximum, then you are looking directly into the horizon. Your eye level, your eyesight is parallel to the x-axis down here. And so we would say that your rate of change is exactly 0. So if this is some function, f of x, then at the maximum, we have that f prime of x is equal to 0. Another way of saying that is dy dx equals 0. These are just different notations to imply the same thing. Well, for multivariable functions, it's the same idea, but we have a rate of change of z versus x, and often we call that dz dx, which is also, we can't write f prime because, well, if we wrote f prime, then it would be unclear whether it's the derivative with respect to x or y. So we write f with a subscript of x comma y, and those two notations are identical. Now, the rate of change, if we look at the rate of change in the x direction, if we're standing here inside of this paraboloid, if we're standing at that point, then we are looking directly, our eyesight is again parallel to this floor, right? We're looking at in both directions, whether we look in the x direction looking this way, or we turn and we look in the y direction looking this way, in both directions our eyesight will be parallel to the ground. So here's the ground, here's our eyesight, and it's directly parallel to the ground. So in the y direction, we have a partial derivative that we write dz dy, which is the same thing as writing f with the subscript of y at x comma y. And at a critical point, which could be a minimum or a maximum, we just call this a critical point to give it a general description, we can claim that since our eyesight is level to both the y-axis and the x-axis, we can make the argument that dz dx is equal to 0, and simultaneously dz dy is equal to 0. All right, so what we have to do, and in this situation, if we had the equation of this parabola, we would find its derivative, we would set it equal to 0, and we would solve for x. So if I gave you an equation for this, then you could take its derivative, you could set it equal to 0, and solve for x. In this situation, we have two components. We need to know the x and the y position at which that point occurs. So let's go ahead and analyze this function. Our function is f of xy equals x squared minus 6x plus y squared minus 4y plus 13. So for that function, I'll go ahead and copy it down here. We're going to compute both of its partial derivatives. Now remember that if you're taking the derivative with respect to x, then you're treating y as if it were a constant. So any term that involves y alone, for example this one, and this one, and this one, those are all treated as constants when you differentiate with respect to x. So the derivative of x squared is 2x by the power rule. The derivative of minus 6x is minus 6. The derivative of this is 0 minus 0 plus 0, because constants have 0 rate of change. If I told you that if I said the function is 5, y equals 5, and I said at what rate does y change, you would say, well, it doesn't. It's always equal to 5. So if all we're doing is changing x, then the value of y remains constant. Now we'll repeat the same thing, but now take the partial derivative with respect to y. Okay, in this situation, we can make the argument that anything involving x is going to be constant, or any term involving x alone, more importantly, is going to be treated as a constant. So that's going to be, this term involves x, and we're holding x constant. We're holding x constant, so the derivative of both of those terms is 0. The derivative of y squared with respect to y is 2y. The derivative of negative 4y is negative 4. And again, we have plus a constant, its derivative is 0. So now what we need to do is we need to solve for x and y. Remember, this is when both partials are equal to 0. This is when we are at a point where the slope in both directions is 0, and therefore we are either at a minimum, like in our example here, or perhaps a maximum. So we solve this system of equations right here. All right, so f sub xy, which is this equation, 2x minus 6, I'm going to set that equal to 0. And I'll just, right over the top, I'll just say set. I'm not saying it's always 0, it's just we are figuring out when, for what x, it is 0. And in the second equation, we'll write 2y minus 4, set that equal to 0. And these are fairly harmless equations to solve. The first one, if you add 6 and to both sides and divide both sides by 2, you get x equals 3. Or you could ask yourself 2 times what number when we subtract 6 gives me 0. Well, 2 times 3 is 6, minus 6 gives me 0. Same thing here. Add 4 to both sides, divide by 2, and we get y is equal to 2. Well, that's exactly the same point here. That's when x was 3 and y was 2. And so now we can say that we have a critical point at x, y equals 3, 2. Now, so far, other than by looking at the graph, we don't know whether this critical point is a minimum or perhaps a maximum. We'll establish that in a later video. But what we can say is that, what is the z-value? What is the z-value at that point? How do we figure out what the value of z is when x is 3 and y is 2? Well, now we can go back to our original function. Remember, this equation says z equals x squared minus 6x plus y squared minus 4y plus 13. So now I can evaluate that for when x is 3. 3 squared minus 6 times 3 plus y squared minus 4 times y plus 13. Here I get 9 minus 18 plus 4 minus 8 plus 13. Negative 18 minus 8 is negative 26. 9 plus 4 plus 13 is positive 26, so I get a z-value of 0. So that just means that we have a minimum located at the point x, y, z equals 3, 2, 0.